Okay. Find the melting and boiling points in degrees Fahrenheit.
You gave it wrong for the first one. So 586.1 minus 32.
Yeah.
586.1
What?
minus 32. So you get 554.1 and you divide that with 1.8. You got what? 307?
Yeah.
All right.
It's correct.
It's correct.
Okay. Mm,
We did it wrong. We didn't have to do the conversion of 586.1 degrees. See, the question says the melting point is 586.1 degrees lower than the boiling point. So if
okay.
I've got the boiling point, which is 444.6, first I'll have to convert that into Fahrenheit,
Okay.
and then from that I have to deduct 586.1 degrees,
Okay.
and uh, that would be the melting point in
Okay.
Fahrenheit. Let's see, this is how it would be done. My bad. Hmm. Why is it not working? Okay, so we are given temperature. Melting point is how much? 444 point.
6.
Boiling point is 445.6.
Yeah.
Boiling point is equal to 444.6 degrees centigrade. So first we need this in Fahrenheit. So it will be equal to 444.6 into 1.8
Mm-hmm.
plus 32.
Okay.
So this will be the boiling point in Fahrenheit.
Okay. Mm, do you want me to do it?
Yes, please.
Mhm. Okay. I got 832.28.
Perfect. 832.28. 832.28 degree Fahrenheit. Now the melting point is said to be 586.1 degrees lower than the melting point. So melting point is equal to
586.1 Fahrenheit.
832.28 minus
No,
500.
800. Uh, Wait, which one are you
So
doing?
so we take the boiling point, and from
The
boiling point we deduct 586.1 degrees.
Wait, what?
Melting point is 586 degrees lower than the boiling point.
So,
See, the boiling point was initially given in degrees centigrade. I
okay.
couldn't have deducted this right away from it.
Okay.
So for that reason, I first converted it into degree Fahrenheit,
Mm-hmm.
the boiling point, and now I deduct 586.1 from it so that I get the melting point.
Okay.
Okay, So from this that I just calculated, I deduct 586.1. The answer will be
246.81.
200.
18.
Excellent. So melting point in Fahrenheit is equal to
246.81.
246.18
Yeah.
degrees Fahrenheit. And now the first part, it requires this melting point in degrees Celsius. So I'll have to convert this Celsius back to Fahrenheit.
Okay.
Hmm. So what I'll do is uh, melting point in Celsius. I'll apply the conversion formula, which will be F minus 32 over 1.8. So 246.18 minus 32 over 1.8.
Okay. Okay. Why is it minus 32?
Mm, because that's the formula.
The formula is plus.
A number, a statement.
What?
The formula is just a statement. Nothing.
Yeah.
Never mind.
So, um, what?
Melting point of sulfur in Celsius will be 118.98 degrees centigrade.
But why did you do minus 32?
Hmm. The reason is that if I have to calculate temperature in Fahrenheit. What I do is I take temperature in centigrade, multiply it with 1.8, and
Okay.
then add 32.
Yeah.
So if I convert it, I mean, if I make this temperature in degrees centigrade the subject, I'll have to deduct 32 from both sides. So it will become TF minus
Okay.
32 is equal to temperature in centigrade into 1.8. And then I divide both sides with 1.8. So it becomes temperature in Fahrenheit minus 32 whole divided by 1.8 is equal to temperatures in degrees centigrade.
Okay.
So this one over here is the final answer for question number 3A.
Okay.
What does it ask for question 3B?
Find the melting and boiling points in degrees Fahrenheit.
Melting and boiling point in degrees Fahrenheit.
Yeah.
So boiling point in degrees Fahrenheit. Boiling point in degrees Fahrenheit. We just calculated. Uh, Here it is. This one.
Which one?
832.28. Because
Um.
this was initially given in the question in
Mhm.
degrees Celsius. So we have
Okay.
already calculated it. So the answer for part B, boiling point in Fahrenheit will be equal to 832.28 degrees Fahrenheit.
Mhm. Mm. Okay.
Okay. And this melting point in Fahrenheit we also calculated over here. This one. Okay. So we'll write the same one. Melting point in Fahrenheit is equal to 246.18 degrees Fahrenheit.
Okay.
Got it?
Yeah.
Uh, is there a next part to it? Now we have to calculate the melting and boiling points in Kelvin. So temperature in Kelvin is equal to temperature in degrees centigrade plus 273.
What?
Part C, we have to find the melting and boiling point in Kelvin.
Mm-hmm. Yeah.
Okay, so first we need to know the formula for conversion in Kelvin. So for Kelvin conversion, we initially need it in temperature in degrees centigrade. So we already have that.
Okay.
So melting point in Kelvin is equal to melting point in degrees centigrade plus 273. So melting point in degrees centigrade is how much? 118.98
Okay.
plus 273,
Um,
which would be 273 or 273.13. 118.98 plus 273.13.
let's see. Yeah, 0.15.
0.15.
Yeah. Okay.
So
I
this gives me answer how much?
392.13.
392.13 Kelvin. And now I'll do the same thing for boiling point. Boiling point in Kelvin is equal to boiling point in Celsius plus 273.15. Boiling point in Celsius is given in the question, which was
Um,
444.6.
yeah.
406
444.6.
plus 273.15, which is how much?
Mm-hmm. 717.75.
717.75.
Yeah.
All right. Any other question involving? Okay, question number 4. Could you read and tell me the answer?
Okay. Okay.
I think we discussed this one in the last class. Fourth.
Yeah, yeah, we did.
Okay, fifth, quickly, if you could tell me the answer.
Two gases that are in physical contact with each other consist of particles of identical mass. In what order should the images shown in Figure 5 be placed to correctly describe the changing distribution of kinetic energy among the gas particles? Which group of particles has the highest temperature at any time? Explain. Mm, wait, this, mm, mm. So, oh, uh, B will have the highest temperature.
Mm,
No.
Okay, the thing is that
Yeah.
the highest temperature difference would be particle has the highest temperature at any time. See, first of all, in which order are the things moving in this particular diagram? Which is the first picture? Which is the second picture? Which is the third picture?
CAD.
Excellent. CAB, and the highest temperature would be in C,
Oh yeah.
because there onwards they would keep on losing the temperature.
Okay.
Okay. Have you ever tried to make popcorn and found that the most of the kernels did not pop? Why do they not pop? Question
Cause,
6.
cause enough heat didn't go to them.
But some they get burnt.
Yeah.
The kernels they pop when there is moisture inside them.
Okay.
Okay. And that moisture, it creates pressure which makes them pop. And if the moisture is missing, they've dried up, then they won't pop.
Okay.
Those are the ones which are uh,
Let me write.
missing moisture in them. Well, लाडा इसको ले जाता है ये उछलेगी हाँ तंग करेगी पढ़ने नहीं देगी Got it, madam?
Moisture. Okay, I'm done.
Okay. Then we move on to the next
Lesson.
what whichever section 2 of your
Yeah.
book. Okay. So now we'll get introduced to the concept of heat. The first
Yeah.
thing is that we have to know what is the difference between heat, internal energy, and temperature. So
Okay.
these are the three terms that we have used, and two of them which we have used in the
Mhm.
last section as well. So my question is, first of all, you'll tell me um, heat, temperature, and internal energy. What's the difference?
What's the difference between heat and temperature?
And internal energy as well. Yes.
Um, Heat is uh like
Okay.
how hot something is.
I mean, how do I know how hot something is? By knowing the temperature. And how do I know the temperature? By internal energy. So internal energy is the total energy of all the molecules within the body, right?
Okay. Wait, can you repeat that?
I'll write it down, in fact.
Okay.
uh, Internal energy is the sum of energy of molecules. Molecules of a substance. Okay. Temperature is the average kinetic energy of molecules. Okay, and heat is amount of energy transferred from one object to another because of differences in their temperature. All right.
Mhm.
Okay. And from the previous chapter, we know that wherever there is higher energy, it would result in higher temperature, and lower kinetic energy would result in lower temperature. One thing. The second thing we know that from bodies of higher temperature, heat flows towards the bodies of lower temperature. For example, if I place a cold cup of water, it may feel like that this cup of water is losing its coldness,
Yeah.
whereas actually things are other way around. The environment of that cup of water is losing its heat energy to that cup.
Okay.
Okay, so it's a flow of energy from higher temperature bodies to lower temperature bodies. That is one thing. The next thing is that so this is for the direction of heat. The next thing we know that this transfer of heat, the change in temperatures or transfer of heat would cause change in temperature, or change in temperature would cause transfer of heat energy. That's
Mhm.
also something simple, right? The third is um, the transfer of heat energy. It depends on the differences of temperature. So, for
Okay.
example, if I've got two bodies, for one, the temperature difference is for body 1 and body 2. So, for body 1, temperature is 40 degrees centigrade, and for body 2 temperature is 50 degrees centigrade, right?
Yeah.
And the other case that I take, again there are two bodies, but let's call them A1 and A2.
Okay.
A1 has got 100 degrees centigrade of temperature, and A2 has got 110 degrees centigrade of temperature.
Okay.
In which case transfer of heat energy would be higher?
In which case heat would be more?
More heat energy would be transferred.
Uh, A1.
Hmm, wrong.
No?
Uh-huh. It would be the same in both, because
Oh,
the difference in temperatures in both cases, delta theta is 10 degrees centigrade, right? So as long as differences in temperature is the same, the amount of heat energy is the same. Another way to understand this thing is, I don't know if you remember from your previous studies or not, work done is equal to change in potential energy or change in kinetic energy.
hmm,
So if a body is dropped from a certain height, at height it has got higher potential energy. When it falls down to the ground, its potential energy is gone. So
yeah.
the difference in potential energies is equal to work done.
Yeah.
Okay, the same way heat, which we show with the symbol Q, is change of internal energy. Q is equal to delta U.
Okay.
Okay,
Mhm.
Okay. Another thing, also from the work and change in potential energy diagram, we know that when, for example, I'm holding a pencil at a height,
Mhm.
okay, and I leave this pencil, it will drop towards the ground. Why? Because it's going from area of higher potential energy concentration to area of lower energy concentration.
Yeah.
It's not that whenever there is a pencil lying on the ground and I open my fingers above it, the pencil, it goes from the ground up to my hand.
Yeah.
Okay, because it won't go from an area or from a region of lower potential energy to higher potential energy. The same as with heat. Okay, this, then the next thing we have is that heat, it has got heat since it's energy, and the unit of energy is
Joules.
excellent.
Oh,
Uh,
okay.
so unit of heat energy would also be joules.
Yeah.
Okay, there is another unit used, which is calories. So calories are less often used, first of all, and
Calories,
calories, calories.
like the ones you eat, like from
The
food.
Yes, exactly. They are mentioned over there to tell you how much energy this food would give you, and
Oh,
it's the same concept when you say that you are going to burn your calories. How much energy are you going to consume?
okay.
Okay, so the conversion between calories to joules is 1 calorie is equal to 4.186 joules.
Do I have to know this?
Since I have got no clue what sort of exam you'd be appearing for, that's why I can't comment.
Okay, I'll just write.
Sure.
Okay.
Okay, and usually for food, you must have noticed that the energy is mentioned in terms of kilocalories.
Okay.
All right. So 1 kilocalorie multiplying both sides with 1,000, I get 1 kilocalorie is equal to 4.186 into 10 raised to the power 3 joules.
10 raised to the power what?
10 raised to the power 3.
Should do you think I should write this?
No need to write this if you can. I mean, it's a simple thing to understand. Multiplying both sides with 1,000, I get kilocalories and joules in
Okay.
this form. Okay. Uh, what you must know, however, is the next thing, which is the ways in which heat energy it transfers between different objects. So
Okay.
basically, there are three ways heat energy transfers. So transfer.
I think I know them.
Hmm.
You want me to tell you?
Yes, please.
Uh, c- convection. I
Hmm.
think.
Correct. Correct.
Uh, there's two more. Radiation.
Excellent. So the first one is conduction. The second one is convection, and
Uh,
the third one is radiation.
okay. Oh yeah, conduction.
All right. Conduction is the simple one and very easy. I mean, they're all easy to understand. But beginning with conduction, we know that all substances, they comprise of molecules. So
Okay.
if I give energy to one molecule, it would excite, and since it has got higher energy as compared to the neighboring molecules, it would pass off the energy to the neighboring molecules.
Okay.
Okay, so this is how metals, they get heated up. If you put a pan on top of stove, initially the portion which is getting the direct flame, that would get heated up, and
Hmm.
eventually it would start passing off heat to the neighboring molecules until the whole pan, it gets heated up.
Okay.
And that is the reason the handles of these pans, they are made of an insulator.
Oh.
Okay, so that energy, if they are made from the same metal, energy, it would get passed to the handle as well, and you won't be able to hold that utensil.
Like wood is an insulator, right?
Hmm. Hmm. Hmm.
Because
So the
I've
reason.
seen those pans with the wood on the
Hmm.
end.
Hmm. 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 So the tawa or the normal, what's
Yeah.
that called? Is it pan or whatever,
Yeah.
used to cook roti? The reason it has got a wooden handle is that if it were not a wooden handle, so for example, for kadahi, you
Yeah.
have sometimes got its ears which are also made of metal,
Yeah.
and they get heated up. So you have to hold it using a cloth or mitten or
Yeah.
whatever. So eventually the principle is the same, that as long as there is a conductor, the
Hmm.
molecules of the conductor, they'll keep on passing the energy to the neighboring conductors, and
Okay.
they'll get heated up. One thing. So one, we know energy transfer to neighboring molecules. This is
Why?
the.
Okay, this is kind of a dumb question, but
It's fine, ask it.
why doesn't heat transfer to insulators?
Mm, uh, you see, science is basically observation.
Okay.
Okay, so when we have done the experiments and we have found out there are certain atoms in which, another reason at the molecular level is that these conductors, they usually have free electrons.
Oh.
Okay, or their electrons, or their atoms, they are packed together.
Okay.
If the atoms, they are packed together, it's easier for one molecule to pass on the energy to the next molecule.
Okay.
If the atoms, they are far away, or they are arranged in a way in which there is less energy transfer from one molecule to the next, those particular substances would be labeled as insulators, since heat is not passing off.
Okay.
Okay, even for insulators, you would notice that if I heat a particular portion of that insulator, at least that particular portion would warm up.
Yeah.
It won't pass on the heat to the rest of the material, but that particular, since I'm providing direct energy, so the molecules that are receiving the direct heat energy, at least they'll get warmed up.
Okay.
Did I answer your question? I mean, is this what we were asking?
Yeah, yeah. This is what I was asking.
Okay. Neighboring
An
molecules. Okay.
example of conduction is like also if you put a match under a spoon, like a
Hmm.
metal
Hmm.
spoon,
Hmm. Hmm.
it the heat conducts, right?
Hmm. Hmm. Correct. Correct.
Okay.
So metals, they are usually good conductors,
Okay.
and that is why all of our cooking utensils, they are made of metal.
Hmm.
The reason they're not made of plastic is that plastic, it won't transfer the heat, or wood, or any other material. Okay, the next thing which is related to this thing that you brought up is that, do all conductors conduct the heat the same way or at the same rate?
No.
So different conductors uh, transfer heat, transfer or conduct heat at different rates.
Okay.
Okay, so for example, silver, I think, is considered the best conductor. So if
Okay.
you use a spoon of any other metal and a
Hmm.
spoon made of silver, and you light a match at the same time under both these spoons, the silver one would get heated up first.
Okay.
Okay, this, then the next method that we have got is convection. Convection, it uses the principle of conduction plus the principle of pressure, for example. Okay, so the way convection works is, if I've got air and I give heat to a molecule of air, or some molecules of air, uh, that get heated up.
Okay.
Okay, then the space between the molecules would increase,
Hmm.
their density would decrease, and
Okay.
then they would be replaced by cooler and more dense air.
Okay.
Since you mentioned in the last class that you know that hot air is less dense as compared to cooler air,
Yeah. Like the
right?
hot air balloon.
The hot air balloon phenomena. So when I heat the air in the hot air balloon, it gets heated up. and then it moves to the top. If it didn't move to the top of the balloon would never lift up.
Yeah.
Okay, so the reason it gets replaced by this cooler air is the reason
Mhm.
that hot air, it keeps on going to the top of the balloon and it lifts the balloon.
Yeah.
That is for convection. So energy transferred. mm,
It's like a continuous cycle, right?
hmm,
Like
hmm,
the ones that are heated go up, and then the more dense ones come down, and then the other ones come up, and the other ones come down.
Correct, correct. The ones that go up, they won't maintain their high, they went up because they had higher energy.
Yeah.
Eventually they'd pass on their energy to the neighboring molecules and they'll become cooler, and then they'd come back again, by which time there would be some more or other hot air hot molecules which would be ready to replace them.
Yeah.
Okay, so in convection we have got energy transferred okay, in conduction material does not transfer.
Okay.
In conduction material does not transfer, material stays right there where it was.
Hmm.
Just the molecules, they keep on passing energy to the neighboring ones. In convection,
Okay.
energy is transferred by transfer of material.
Okay. I heard that microwave is an example of all these ones.
uh yes, we'll see how.
In a
We'll see.
way. Like I heard.
Hmm. You're right, you're right. Okay, so this mechanism of heat transfer makes use of principles of pressure. I mean, obviously, the phenomena of heat plus the phenomena of pressure, and other than that, it uses conduction and B U O B U O Y A N C Y buoyancy. Mhm. Okay. The third method of heat transfer is what we call radiation, and
Okay.
the most, I mean, the striking thing about this particular method of radiation is that this method, it does not require a medium to transfer heat.
Okay.
One thing. Uh, so if you imagine that in between the sun and the earth there is space,
Hmm.
and space is literally space. Do you know what is space?
Yeah.
Spaces that there is nothing in it, no matter, no air, no gas, nothing.
Yeah.
So sometimes when we imagine about space, we might think that there is air up there. There's not
Okay.
even air. There is no matter over there.
In space,
Hmm.
don't they have like gases?
I mean, if there were gases, then why would it be space? Where does
So
it get its name space from? So there is
in
actually
space, there are no gases.
a gap between the sun and the earth where there is no matter,
So there's no gases.
no gases. Okay, it's a bit I mean, if it were simply gases, then the energy from sun to earth, it would transfer by conduction or convection, but it
Okay.
gets transferred by irradiation. And then, I
Oh,
mean, if there is no matter, or if there is no gas or liquid or solid, then it means there are no molecules.
okay.
Okay, if there are no molecules, if you see both these methods of conduction and convection, they make use of molecules at some level. So
Hmm.
either energy is being passed off to the neighboring molecules, or the molecules themselves move away to make room for other molecules to come in, right?
Okay. Yeah.
So in radiation, the way energy transfers is by electromagnetic radiations.
Okay.
So energy transferred by electromagnetic radiations. Okay. Have you studied the topics of electricity and magnetism at your school?
Yeah.
Okay, so if you have, you must have noticed that electricity and magnetism usually they exist together. Electricity gives rise to magnetism, and magnetism it gives rise to electricity.
Hmm.
If there is a current passing through a wire,
Okay.
it would create a magnetic field around it.
Hmm.
And if I move a magnet around a wire,
Okay.
it would create electricity in that wire.
Okay.
What we call electromagnetic induction. Okay, so the point of bringing this up right now is that we have got a field. uh, I mean, how does energy transfer from the sun to the earth if there is space in between? It transfers as electromagnetic radiation.
Okay.
Okay, and for electromagnetic radiations to move around, they would need an electromagnetic field through which they
Hmm.
travel. Okay, 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 okay. Hmm. So how is energy transferred? Uh, Number three, the third point I'd write over here is that uh, particles, particles, sorry, objects, objects reduce their internal energy by giving off electromagnetic radiation.
I can't see this part.
Mhm. I'll move the screen now. Electromagnetic radiation of particular wavelength. Do you revise what we studied during the class after the class?
Mm,
You
yeah.
should.
Yeah.
So it's just that objects either they are giving off their energy in the form of electromagnetic radiations, or they are absorbing electromagnetic radiations from around,
Or what's the last part?
or are heated by electromagnetic radiations.
Mm.
So the same way a car standing in the sunlight is heated up by sunlight because it is absorbing the electromagnetic radiation from the sunlight.
Yeah.
Okay, this then maybe one last thing that we need to know in this particular topic is that total energy of a system is conserved. So if there is change in potential energy and there is change in kinetic energy,
Oh,
okay, if I add to that the change in energy of the system, the answer would be zero.
yeah.
Because if there is positive change in potential energy or positive change in kinetic energy, then something it must have lost energy to make sure that these two they gain energy, these two. Anyways, this is the equation that you need to know. And for change, you know that to calculate change in potential energy is equal to final
Mhm.
potential energy minus initial potential energy, right?
Yeah.
Change in kinetic energy
Is
is equal to
P
ke
final minus P initial.
ke initial, excellent. And change in total internal energy would be equal to u final minus u initial.
Yeah.
All right. Shall we do the question of this topic as well?
Yeah.
Mm, Let me check if your book mentions this thing. Mm, mm, mm. This we have discussed. This we have discussed. Heat and work we have discussed. Um, Conservation of energy. Let's see. Let's see. Okay, so this problem over here, an arrangement similar to the one you can see my screen, right? It's just your book.
Yeah.
An arrangement similar to the one used to
We
demonstrate.
actually for this one, let me check. Wait. We don't have to do this. Actually, no, no, no. We can do it. It's fine.
Okay, okay. A vessel contains water pedals that are propelled by falling masses turn in the water. So these
Okay.
masses that make these pedals move. Okay.
Mm-hmm.
This agitation warms the water and increases its internal energy. Obviously, this movement of water, these pedals moving inside it, would create energy.
Uh-huh.
The temperature of the water is then measured, giving an indication of water's internal energy increase. Okay, so all this energy which is caused in the water, increase in internal energy means there is heat energy in the water.
Mm-hmm.
I mean, internal energy of the water is increased. It's due to movement of molecules, and average kinetic energy of the water has increased. So there is heat energy in there, right?
Yeah.
Okay. This gain in energy of the water, it would be, where does it come from? It comes from these pedals.
Mm-hmm.
And where does energy in these pedals come from? It
I
comes
have
from
no idea if this is coming in the exam because I feel like she said this type of question wouldn't come, but I don't know.
all you need to know from this thing is that energy in a system, even if this question doesn't come, I'll just quickly wrap it up.
Okay.
Even so energy anywhere, if there is change in energy in water, it must have been caused by change in energy somewhere else.
Okay.
Okay, so we are asked to calculate change in energy in water. What's the change in internal energy? And the only other change in energy that we have got is because of these masses. So these masses, they'll give me change in potential energy. Potential energy is calculated as how? Mgh.
Yeah.
Okay, so if I simply apply mgh on this mass, it would be equal to the change in internal energy of the water. I'm not going into complexity of this equation. We can save this for the next questions that we'll have to do at the end of the chapter. That's it. That's the end of the chapter. These conservation energy
Mhm.
problems.
Yeah, I've done some of these, I think.
Could you tell me which one you have done?
I don't remember which ones exactly
Uh,
because my book isn't
sh-
with me.
okay. Shall we do all these in the next class then?
Yeah,
Okay. We'll start from here. We'll just quickly go through these questions and then move on to the next topic. Uh, okay, section review as well. Would be really
yeah, I
helpful if
did.
you. Hmm? Hmm. Go ahead.
Yeah, I did